Hey guys, welcome back to Genius Learning. In this video, I want to take a look at constraints that we need to find in a Lagrangian system. Okay, so for this particular system here, we have a particle that is allowed to rotate or move or spin or inside of this cone, right, and not outside of it. Okay, so the distance from the center of the cone to the particle is r. All right, and we're constrained to that movement. So we can't leave the distance of this edge here. And so once we get to the bottom, the r is going to be smaller, or if we're rotating at the top, we're spinning, with some omega up here, then the r is going to be bigger. So let's look at why our constraint is going to be what it is. So if we look at this, so this is going to be the same picture here. This distance here is r, right, which is the same r as this one. And I want to look at this side right here. So let's focus on this triangle over here. Right, we know that the angle made from z going down to the xy plane is theta. Right, I'm going to label this side here z. All right, and then let's label this hypotenuse side s. Okay, so this is a right triangle. And so just to show that this is the right triangle, we got s squared is equal to z squared plus r squared, right? So that's the triangle that we're looking at. So we're constrained to move within this cone. And remember, this angle here doesn't change. All right, so this cone is fixed and the particle is spinning inside of it. And so we can spin towards the top, or we can spin towards the bottom or in the middle. All right, so we're restricted to move, and this is our restriction right here. Tangent of the angle is opposite over adjacent. All right, this right here is our constraint. This basically means that this distance r could be smaller or bigger, this distance z could be smaller or bigger, and the angle that we're restricted to is this one right here. Okay, so if we rearrange this, we can find z is equal to r over tangent theta. And using trig, we know that 1 over tangent is cotangent. So really what we have is r cotangent of theta. Okay, and remember that this theta here does not change. Does not change. Okay, so that's important when we go to do our derivatives. Okay, the r does change, so the length of this r does, but the theta does not. Okay, so now that we identified our constraint, let's look at the position of this particle right here. So we can model this as a cylinder, right? And let's project this particle down onto an xy plane. Okay, this r here, we're gonna also project down. So this r here is the same thing as this r up here. Right, and then we know that the angle on the xy plane is phi. It goes from x to y and all the way around. So using this angle and this hypotenuse here, we can do opposite over hypotenuse, which is this side right here. Okay, and we can also do adjacent over hypotenuse, so that's adjacent over hypotenuse represents this side here. Okay, so this side is also the same thing as this side. This side here is also the same thing as this side. And we found over here our z. So this height right here, our z, is going to be r cotangent of the angle, which is this angle here. Okay? So that means that our position for the particle is going to be x equal to r cosine phi, y is going to be equal to r sine phi, and z is going to be r cotangent theta. All right. So now let's take a look at our velocity. Okay, so the velocity of this particle, right, we just take the derivatives of the position, but we have to keep in mind and understand what's changing and what's not changing. So r is a function of time. So really, this is how the notation is, right? Because this r could be smaller down here, or it could be bigger up here, depending on where the particle is. And phi is also a function of time, because if the particle is on this side, you have a certain phi that represents it. But if the particle is all the way back here, or even on this side, now the phi has to go and sweep around the xy axis on this side, and so the phi is changing. Okay, so these two things are changing. Theta, which is the angle of the cone, does not change. Okay, so this shape of the cone does not change. It's a fixed cone. And so this does not change. So there's no change. It's not a function of time like these. All right. So with that in mind, let's take the derivative of x dot. Okay, so we have a product rule, right? Because both of these are a function of time. And so for, let's separate this. Okay, product rule. We do the derivative of the first, the second comes along, plus f, which is the first one, and then the derivative of the second one. So r dot, we take the derivative of it, we leave cosine phi alone, and then it's going to be plus, right? But I already know that the derivative of cosine is going to be negative, so I'm just going to write a negative there, right? We leave the first one alone, and then the derivative of cosine is sine phi, which is negative sine phi, phi dot, right? We need to do the chain rule because the angle is inside of the cosine. Okay, so now y dot is going to be the same thing. We got r dot, we leave sine alone, plus r, and then we do the derivative of sine, which is going to be cosine phi, phi dot. Okay, and now for our final one, it's z, and z we know is r cotangent of the angle. But remember, the angle is not a function of time. Okay, so only the phi angle is a function of time. Theta is not a function of time. So the only thing we take a derivative of in here is r. So we have r dot, and cotangent theta stays the same. Perfect. So now we have our position, we have our velocity. Let's look at our kinetic energy. So we know that kinetic energy is 1/2 mv squared, which can be written as 1/2 m x dot squared plus y dot squared. So this is a general form if we have a 2D system, but in our 3D system, which includes a z, now we have to write it as x dot squared plus y dot squared plus z dot squared. All right, so this is what we're going to be using. This is for 3D, this is for 2D. All right, so let's write t equals 1/2 m. Here we have our x dot. We have r dot cosine of phi minus r sine of phi, phi dot squared, plus our y is going to be r dot sine phi plus r cosine phi, phi dot, everything squared, and plus our last term z which is going to be r dot cotangent theta squared. Okay, so let's simplify this inside here, and I'm going to do it in a different color here so that way we don't get confused. Okay, so I'm going to do this here first. So we're going to have r dot squared cosine squared phi minus r phi dot r dot cosine phi sine phi, and we can put a 2 there in front of it. And then this last term here is going to be plus r squared phi dot squared sine squared phi. All right, that's this right here is all from this first term here. Now I'm going to write this term here underneath it. Okay, so r dot squared sine squared phi plus 2 r phi dot r dot cosine phi sine phi from the combination of these two, and then the last term is plus r squared cosine phi squared phi dot squared. Okay, so I'm just going to simplify some of this first before I continue with the last term here. All right, so I see that this term is the same one as this with the opposite sign, so that cancels out. And sine squared phi, cosine squared phi, and they have the same variables in the front, so I can write that just once. And then I can do the same for sine squared phi and cosine squared phi. Okay, so let me do that and rewrite everything. So we got t is equal to 1/2 m. I'm gonna write these two things first. So we got r dot squared. All right, the cosine squared and the sine squared make a 1. And then we got these two terms here. So I'm gonna write r squared phi dot squared, right? The sine squared and the cosine squared make a 1. And then finally we have here plus r dot, so let's close this off here first, right? Because these two things here, right, were here in black, and this 1/2 here needs to distribute all the way back here. So let's see, 1/2 m r dot squared cotangent squared theta. Okay, and we can also combine this r dot, sorry, this is also squared for the r dot squared. So we can combine this r dot squared and this r dot squared. Okay, so let's distribute everything out. So 1/2 m r dot squared, for this we distribute it into this one, 1/2 m r squared phi dot squared, and we distributed already into the third term, right, that m over 2, so plus 1/2 m, we have r dot squared cotangent squared theta. All right, so if we combine this term here and this term here, right, let me write on the side what we're gonna have. So we're gonna have 1 plus cotangent squared theta. All right, so using trig, we need to identify what that is. So if we do sine squared theta plus cosine squared theta is equal to 1, we need cotangent, which is cosine over sine. So let's divide everything by sine squared. And so we're gonna have 1 plus cotangent squared theta is equal to cosecant squared theta. Okay, so this is what we need. And now we know this really means cosecant squared theta. Okay, so now let's use that when we go to simplify this term here. All right, so let's combine this one and this one here because we have r dot squared. So we can take out 1/2 m r dot squared common from both of these, and we're left with 1 plus cotangent squared theta. All right, so if I pull out 1/2 r dot squared from this term, I have 1 left. And then if I pull out 1/2 m r dot squared from this last term, I'm left with cotangent squared theta. So we derived here cosecant squared theta is the same thing as 1 plus cotangent squared theta. So this we're going to replace with cosecant squared theta. All right, so finally, right, this is the term that's left. So let's write that over here. We have plus 1/2 m r squared phi dot squared. All right, and so finally we have t is equal to 1/2 m r dot squared cosecant squared theta for this term plus 1/2 m r squared phi dot squared theta. Phi dot squared. Okay, and this is our kinetic energy term. All right, so it's a little bit tricky. Once we distributed everything out and canceled what we needed to, we're left with these 3 terms. Okay, we can combine r dot squared and r dot squared. So we're left with 1 plus cotangent squared. And then knowing our trig, we identified that it's cosecant. So we simplified it further, and this is our kinetic energy term. All right, and so then finally, our potential energy is going to be U is equal to mgh, which is the same thing as saying mgy, or the height, but this is in 2D. So for this problem, we're going to use z because this represents the height. Okay, so we know our z is r cotangent, and so then we have u is equal to mg r cotangent theta, and that is our potential energy term. Okay, and so then finally, to write the Lagrangian, I won't do it in this problem, but the Lagrangian is just the kinetic energy minus the potential, and here you have both. You have your kinetic energy term minus your potential energy term, and then you have constructed the Lagrangian. Okay?